Hello, Chem 1A. This is Chapter 8, Lecture Video 2, and we're going to be discussing how to calculate the energy of a photon of light. So, the amount of energy in a single particle of light, i.e. a photon of light, can be calculated using this equation. This equation is known as Planck's law, developed by a famous scientist or famous physicist / scientist, chemist named Planck, last name Planck. The h here is a constant, which since, Planck came up with the equation, he gets the constant named after him as well. It's Planck's constant, and it's a constant I'll provide to you. You don't need to memorize it. New here is our frequency, right? Using that same variable as in the last lecture video. And this equation you do not need to memorize. I'm going to provide it to you, just like I'm going to tell you that h, or Planck's constant, is 6.626 times 10 to the negative 34 joules times seconds. Those will be given on your exam. Another equation given on your exam is going to be C is equal to lambda times nu, which is our equation of the speed of light. And that's something I'll also provide you. I will also give you the speed of light as a value on your exam equation bank as well. All right. So let's talk about that. We have this equation. This is Planck's law that we just learned about. And we also have another equation, and that is that C is equal to lambda times nu, right? This was that first equation we talked about, and it's how light can be described in terms of the speed, the wavelength, and the frequency. Now I can rearrange this equation to solve for frequency. If I divide both sides, for instance, by lambda, then I get that frequency is equal to the speed of light divided by wavelength. Now, if I take this and I plug in to here, I can get another equation, which is that your energy of your photon is equal to Planck's constant times speed of light divided by wavelength. Or it could be just Planck's constant times frequency. Depending on what you're given in the problem, you might use one or both of these equations, or more likely just one of them. But if you're given wavelength, for instance, I'd probably use this equation. But if I was given frequency, I'd probably use that equation to solve for energy of my photon, which is what both of these can do. Now, at the end of the day, we talked about this on the previous 2 slides back. Frequency and energy are directly proportional, and our equation here depicts that, right? Because as my frequency here goes up, my energy goes up. So the other thing we learned was that wavelength and frequency are inversely proportional, and this equation down here depicts that as well, because as my wavelength goes up, my energy goes down because it's in the denominator. Again, you need to know that these two relationships are the way they are. So energy and frequency, we need to know they're directly proportional, and that wavelength and frequency are wavelength and energy are inversely proportional. Okay, so let's finish this lecture video off with an example problem for the energy equation. So we want to know how much energy in joules is present in a single photon of light at a wavelength of 540 nanometers, right? And in addition, we want to know, hey, how much energy is in a mole of photons with a wavelength of that, right? So let's do these problems out, right? So let's start with the first one. We'll just do this one first and then do this one second. They're separate problems. So I know that energy is equal to Planck's constant times speed of light over lambda. We saw this equation on the last page. I'll give it to you on the test. You don't need to memorize it. We also know that speed of light is 3.00 times 10 to the 8 meters per second in a vacuum. And we're always going to be in a vacuum in this case. And Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. And that's another value I will provide. So using these two and the given wavelength here, we can solve for the energy of this photon of light. Now, it's very important that you understand that this is in nanometers and this is in meters, and these two units do not comply with each other. So before I can plug these two values into my equation over here, I have to convert units. Now, it doesn't matter if you convert this to nanometers or this to meters. Pick one. Do that. All right. I'm going to convert nanometers to meters. So I know that 540 nanometers, and if you can't remember the nano prefix, get that metric prefix back memorized because you should know it. I know that 540 nanometers, that relationship between meters and nanometers is that 1 nanometer is 1 times 10 to the negative 9 meters. And this gives me that I have 5.40 times 10 to the negative 7 meters. Now I can solve this equation, right? So E is going to be equal to 6.626 times 10 to the negative 34 joules times seconds times 3.00 times 10 to the 8 meters per second. And seconds here will cancel with that. And I need to divide this all by 5.40 times 10 to the negative 7 meters. So meters here cancels as well. And we're left with just joules. So if we do this calculation out, we get 6.626 times the speed of light divided by 5.4 e to the negative 7. And this gives us 3.68 times 10 to the negative 19 joules. This equation is always only for a single photon of light. So this is our answer. And we're all done with this problem. So let's talk about this problem. I'll use different colors. So again, we're going to use that same equation. I do need to change 320 nanometers to meters. Again, we could use this version of this metric prefix. There's another way to write this, though. If you wanted to, you could say 1 times 10 to the 9 nanometers are in 1 meter. Pick your pleasure. Memorize the unit factor one way and solve for it that way. This gives me 3.2 times 10 to the negative 7 meters. And so I know that E is equal to, again, 6.626 times 10 to the negative 34 joules times seconds times 3.00 times 10 to the 8 meters per second, all divided by now 3.20 times 10 to the negative 7, because I'm at a different wavelength. And again, my meters cancel, my seconds cancel. I'm going to be left with joules. I should know that the energy I get here is going to be larger because my wavelength is smaller. And that's what I see when I do the calculation. And we get 6.21 times 10 to the negative 19 joules. This value is larger than that value as I predicted. But this is still just for one photon. So I wasn't asked for one photon, I was asked for a mole of photons. So I know if every one photon has this much energy at this wavelength, then what I can do is 6.21 times 10 to the negative 19 joules, and we can write it as over one photon if you want. It kind of helps. I know one photon. Sorry, wrong. I know that 1 mole of photon, because I want it per mole of photons now. I know that in 1 mole of photons there are 6.022 times 10 to the 23 photons. This is Avogadro's number. And so, again, we get photons canceling, and we're left with joules over moles of photons. And this answer, I'm going to write it over here, is going to be equal to a pretty dang large number, right? 1, 2, 2. And we get 374. I'm just going to round to 3 sig figs because that's really all I should have anyways. Joules per mole, or 374 kilojoules per mole. And these two are my final answer for the second question. This was the first question. And that's the end of this lecture. If you have any questions, please don't hesitate to ask me via email or my office hours.